everybody. This is Power Move. My name is Caleb.
I'm Linnea.
You're not. Oh, I'm Aaron.
Calvin?
Zach.
So, just a recap, we are a team that does an exoskeleton, and currently we are having our problems running into several issues. First is the cost, second is the weight and the size. So, on the next slide, I'm going to talk about the changes that we did. So previously we were targeting our audience towards a moving company like U-Haul. So U-Haul, you get this exoskeleton we made and then give it to the customer. They rent it out, and then that exoskeleton is basically help you lift stuff and also exceed more strength. But what went wrong during the analyses are the systems are just too heavy and too big for an actual person to wear it. It's not actually helping the people to move. So what we did right now is we target our audience into a warehouse worker. So we change our system. Instead of wearing everything at the back, we're going to change it to a cart system. So what's a cart system? A cart system is like you'll have a cart right here. All you have on you is just the cylinder right here, and all of the stuff will be on the cart, like the motors, batteries, accumulator, those kind of stuff. And these will reduce a lot of weight. Not just, I'm not talking about half, it's more than half. And the cart also acts like a work table, or also as a warehouse, you know, we move a lot, right? So you move around, you can also put the stuff on there. But now then you will start asking, then why don't we just use like a car or actual machine to lift it? So I'll say that human link is the strongest in here. We have the intelligent instincts and the reflex to do all these movements because we are born that way. And machine is here to provide us more strength and precision. So this just, what we want to do is 1 + 1 is more than 2. So that's our main goal right here. So our target audience is probably going to be more like a warehouse company like Amazon, Costco, Target, IKEA, those kind of companies right there. Currently there are 647,000 people working in Amazon around the world, and every 100 workers in America, Amazon have like around 10 people injured, not just bad, any kind of injuries. And currently in the warehouse segment in the United States, there are 125,000 Amazon employees right now. And then these are the Costco's data right now. And then we're not just targeting our targets in America, we also want to target it in other countries like China, because China's got 10 times more numbers of factories than US. Imagine Indonesia, Thailand, these kind of countries right there, they have a lot of traditional industry right there. They have a lot of heavy lifting duties over there. And according to the statistics, every 5 warehouse workers have 1 back injuries.
All right, so here's just a reminder of our proposed critical path device. We've changed it up because basically right here we have planned that everything is going to be going into the frame, which is going to be on the person's back. And as Aaron was saying, this device weighs a lot, and we don't want to be putting 50 pounds on the back of a person if they're going to be wearing it all day, especially if it was for the general public, which was our proposed audience. No one wants to lift 50 pounds when they're trying to make weight lighter for themselves. So this is what we originally had planned, and our current fall quarter RFP follows the orange arrow, which I will be showing to you in a slide very soon. Okay, so here it is, our proposed critical path device. Here's our system design right here. It consists of a shoulder mount and a receiver pin that goes through a 4-bolt bearing flange, and it's going to be receiving its signals via a MyoWare microcontroller, or MyoWare is going to be sending signals to a microcontroller, and that's going to be sending signals to our actuator, or to our, oh my gosh, to our microcontroller to send a signal to our pump, or our valve, that our actuator should be moving. And that's going to be coming from a band that's on the bicep, so the signal should be strong and it should be quick. All right, so here's our mechanical risk reduction prototype. And in a little bit more detail, this is what we've got running right now. We've got our reservoir, and the reservoir is going to be flowing through our filter, which is this white guy right here, and the filter is going to go to our pump, and as it spins, it's going to be pumping fluid through past the pressure transducer into our accumulator. Our accumulator is going to charge up fluid, and it's going to build pressure. And once our system is charged, that accumulator is going to release fluid through this open valve, this valve shut, and it's going to go straight into our hydraulic cylinder. And that's going to fill up. As it fills up, it's going to extend and it's going to retract a person's bicep. Now, once we're ready to extrude and push this, or I guess contract and pull this back in, the person will simply drop their arm and it's going to push back on the cylinder, allowing fluid to flow back. This valve will shut and it will allow our fluid flow back into our reservoir. We have a relief valve as a safety mechanism in case we increase pressure beyond what we have expect or anticipate, just in case, and it will flow right back to our reservoir. And our pressure transducer will be our signal that we are actually reaching a point to where it's unsafe, or the pressure is exceeded and we don't really want to go any further. And that would technically communicate back to the pump, which is running off of an ESC battery, which is telling it how it needs to be spinning and the timing, all that.
Hello. So for the electrical risk reduction prototype, so we essentially started with a force sensor, which is can sense up to 30 kilograms. Having talked to Dr. Arabian during the course of Senior Design 1, we changed our direction from using the force sensor to the Myoband, which he had provided. Later on, we discovered that if Myoband already been programmed, it will be close to, it will be very difficult to program. Not only that, even if we programmed it correctly, still there are some bugs that might occur every now and then, which is going to be a risk for our systems. So now we decided to use a MyoWare, which is basically is going to be a MyoWare, which is going to send the signals from the muscles to back to the microcontroller, which is going to be able to send the signals to the two-way valve and our hydraulic actuator.
Alright, so these are our specifications for our RFP on the mechanical side. We decided that we wanted a hydraulic actuator force output of at least 1 pound, and ideally at least 13 pounds. We wanted the weight to be lower than 10 pounds, or ideally lower than 3 pounds. And we wanted 1 movement per minute or 3 movements per minute. And these were all chosen assuming that we would be building a miniature hydraulic device. So we wanted our force to be less than we actually needed it to be, and we wanted the weight to be much less than we actually needed it to be. However, through the course of the quarter, we've been researching materials and components that we need to buy for the hydraulics, and it was actually much less expensive to build our full-scale hydraulic with one actuator instead of doing a miniature hydraulic system. So we're going to be not meeting the weight spec, but we definitely met our actuator force output and
Go back. So I forgot kind of to mention that this one we're testing the force sensor here. Those actual data is the force sensor for the MyoWare, due to the fact that we already have the MyoWare ready here, but we don't have the electrode dots, which is connect the MyoWare into our arms. So we're still waiting for that, but we're just going for the assumption it's going to work, or it's going to give us a strong signal as the effects.
Alright, so this is proof that we met our force output for the RRP. On the left here, we have the actuator just standing upright with 13 pounds on it, and on the right, it's extended fully, about 4 inches, and it still has that 13 pounds balanced on it. Khaled's hand 12 seconds to actuate fully, and then from there, we open our valve to let the weight fall back down, and that takes less than 8 seconds. And this is actually a little bit of a slower process than it should be right now, because we chose a pressure relief valve that has a lower pressure than it should. So our pressure relief valve actually will release pressure from our system when we're moving this up, unless we have the end of that capped. So this process of testing movements per minute had us capping the end of the pressure relief valve hose, moving the actuator, and then for releasing it, we would have to take the cap off, open the valve, and let it fall, and then put the cap back on before we make our second actuation. So when our pressure relief valve is at a higher pressure, like it's going to be next quarter, this process will be a lot faster because you won't be taking a cap on and off of the system.
And for the critical design specifications here for the data processing, it's we met the spec again. We're using the force and stuff with the microcontroller. Definitely is less than 100 milliseconds, and we're meeting the threshold. The only point I'm trying that I should make here is that the MyoWare should be more accurate and much faster processing data than the processor. And for the verification of the data processing speed for the microcontrollers, I'm using Allegro that should be compatible with MyoWare. It should also be expected to meet all of those expectations in terms of the thresholds for the 100 milliseconds, and it's definitely so we're definitely we're going to be able to meet that. With the start of the winter quarter, we'll get the actual data.
All right, so this is an overview of our engineering analyses. We'll be going more in depth throughout pretty much the second half of our presentation, so I won't really bore you with the details of those right now. But this is just going to be a good layout of what to expect in the next few slides.
For the power consumption, keeping in mind that there are some steel department having been ordered for the winter quarter, so it adds up to 372.75 watt. So we need at least a battery that can supply 372 watt plus 15 amps. When we tested our hydraulic system, we were under the impression that it only needs 12 amps. As a matter of fact, it turns out to need 15 amps. That's why we had to increase the voltage in order to get the motor to spin fully. And for the data acquisition speed, as I mentioned earlier, we're expecting all of them to meet the thresholds. And just need to mention this is 1 second for if it's greater than 1 second, it will be readable by human, and that is we're trying to avoid that.
So for structural analysis, here we have our CAD of our shoulder mount, and so we've got our shoulder mount here, which we've got we've done an FEA analysis on, as well as our receiver. And so amongst our FEA analysis, we have determined that we have a factor of safety of about 5 if the material is aluminum 5052H32. And so given that, we're feeling pretty comfortable that we have a pretty good margin of safety. We would like to start to cut down our shoulder mount a little bit so that we can start saving weight. As we said, this is a very heavy design, and so we're going to try and save weight as much as we can. Another thing we're going to do is we're going to try and implement carbon fiber. As it is more expensive, it should be able to still withstand the amount of forces that we're going to be putting on our framework, and hopefully we'll be able to achieve a lighter weight as possible. I believe the shoulder framework will be about 5.7 pounds.
Great, so this takes us to our weight analysis. This was kind of a simple analysis. We just had to weigh each of our parts. You can notice here that the cylinders and the accumulators, that's kind of the bulk of the weight for our proposed device. They take up about more than half of what the actual device would weigh. So we haven't found out, we haven't decided on the size of the battery, so we don't know how much the battery is going to weigh, but if we exclude that, the whole weight of the device is going to be about 57.5 pounds, which is a large amount of weight for someone to carry on their back, and it kind of defeats the purpose of the project, with the whole idea of being able to increase the maximum weight that a person can hold. If they already have to hold 60 pounds on their backs, it's kind of irrelevant to only give a 40% or 40-pound benefit from wearing that. We also decided here the kind of the layout of our design. So the cylinders, they have to be in these positions because that's where we're going to be getting our mechanical advantage. So there really wasn't a choice on that. Everything else here, though, we wanted to have our heavier parts down lower on the back where the core is. So that's going to be our accumulator and our battery, as well as the motor. We'll have that lower so then it can be supported by our hips and our waist a lot easier. We had our reservoir, our filter a little bit higher because they're not quite as heavy. We also had the space here because we didn't want them to interrupt the kind of muscle activity that's happening right there. There's less muscle activity up here and down here, so we wanted to have that kind of free space so wasn't irritating the back as much.
So for biomechanical, what we did is each of our group member will try to carry heavy stuff around the classroom and see which muscle will be the first to get tired. And it turns out we have almost the same results. Our arms will be the first one to get tired before the legs, and the strain will start getting after the arms. So afterwards, we went to Dr. Kenneth Van to prove that if we're right or wrong. Actually, we're doing pretty good because he said that actually lower body has 60 to 70% more strength than the upper body. So as a result, what we think is just make sure to distribute all the forces out. But now, since we're using like a cart system, most of our weight will be on the cart instead of on our back. Right.
So based on the bioanalysis, so we conducted this study. So we placed, based on Dr. Calvin advice, so there are two kind of people with the short hand and people with some more longer hand. So we kind of conducted this starting with a weight of 40 pounds and putting it in this position. If somebody with a shorter hand, he needs at least 139.9, almost 140 pounds to lift that weight. And for somebody with like a longer hand, he needs 271 pounds. And for in terms of the pressures, the person with the shorter hand needs 140.7 psi, and the bigger person with a longer hand needs a little bit more than that, which comes to 273.3 psi.
So now we're on a motor-driven pump speed analysis. Our goal is to have 3 movements per minute, and this is the equation we use. As a result, in order for 3 movements per minute, we need this much liter, 1.2 liters of, is that right? Yeah. So, but then our RPs just say 1 movement per minute is fine, so we're just gonna keep it right now. Oh. And now motor torque required analysis. This is the equation we use right now. After using the equation, this is the result. We got 0.146, but we're not too worried about this because we purchased our motor and pump as a package, so we don't really need to take into consideration of this analysis actually.
Great, so another analysis that we had to do is figure out the size that our cumulative needed to be in order to keep the system pressurized while we're actuating our cylinder. So using this equation that we found online, turns out that for a pressure difference of 50 psi, the accumulator needs to be at a size of 9.1314 cubic inches. Yeah, so that's the rate, the spec that the accumulator needs to be. The actual volume of it needs to be 0.24 liters, and that's just doing an analysis of how much fluid is going to be going through our system. Unfortunately, right now our current accumulator is only 0.7 liters, so it's a little bit shy of that, which just means our pump needs to work a little bit harder than we would like it to. Yeah. So as I was mentioning earlier, we have a fluid reservoir size. Basically, we just took all the volume of all the parts that we're going to be using. So the volume of the cylinder and the volume of the accumulator and the filter and the piping. And that has to be our baseline for how much fluid we need in our entire system. Doing a little research on a general rule is that the reservoir needs to have about 5 times the amount of fluid that the pump will flow. And so, yeah.
So for the heat dissipation analysis, we actually have 2 different things that are going to be putting heat into our system. And the first of those is the pump. Pump inefficiencies will cause a rise in pressure. So we took a worst case scenario where all of the power that the pump is consuming is turned into heat, which will actually happen because you're also generating a pressure difference. But this is a very worst case scenario. And we calculated the energy that will be added to our system. And then from that, calculated the temperature rise to 8.61 degrees Celsius over 4 hours. So it's really not something we're super concerned about for the pump inefficiency. For the head loss, that's basically heat transfer that would happen due to the friction in the pipes. So we calculated that with our generic head loss equation from fluid dynamics. And then from that, we turned that into a potential energy that's going to be added to the system. And we have that in terms of specific energy there, joules per kilograms. And then using the same heat transfer equals MC delta T equation, we got a rise in temperature of a very small amount of degrees Celsius per cycle. And then using our number of actuations per minute and the size of the actuator, we found out over 4 hours what the actual temperature rise would be. So the total is that we're looking at less than 1 degree of temperature rise for the entire fluid over the course of 4 hours. So we're really not concerned about our system overheating because of that.
Oh yeah, that's good. So because we are kind of changing our project a little bit due to the total weight of our system, we have proposed to put a lot of the components of the hydraulic circuit onto a cart that can then be used as like a workbench or just a mobility device for an object that we're moving. So we kind of changed our block diagram a little bit here. The main difference is we broke the hydraulic circuit into 2 portions. The top part here is going to be what's actually on the user. So that's going to be the hydraulic cylinder and then just the kind of the hosing and the relief valves that's coming off of that. But you can see here that the bulk of the system is actually going to be on a cart, which is this lower section here. So that's going to include our transducer and our pump and our battery and our accumulator, which that way all adds up. Another difference is that we're going to be using a MyoWare instead of a force sensor. So that's a change too. We also took out the force, the voice control. So going forward, kind of like an ideal project if kind of cost wasn't a limit, and we're predicting that because we're looking at bigger companies like Amazon or Costco, they have a lot more income, that the cost won't be as big of a deal as it was before with a U-Haul company that would be renting out the product. So we did some research to figure out, okay, how can we reduce the total weight of this product? And we found that we can actually buy these aluminum cylinders that only weigh 6.5 pounds versus the 14.6 pounds of our current cylinders that we have now. So a significant drop. The downside of that though is the cost went up significantly. It's about $812 per cylinder, which is a big deal. So going forward for our senior design, we'll just be using the steel ones. We also, assuming for our shoulder mount frame, instead of using a steel for that, we could change the material to carbon fiber, which will also decrease the weight as well. But it also, in turn, increases the price. So we can get our whole system that's mounted on a person to be only about 18.7 pounds versus what it would be with the steel cylinders and the steel frame. It would be somewhere around 35 pounds. So it's a significant decrease in weight, which makes the overall use of this project way more achievable.
And finally, for our winter break, we've got quite a few things that we didn't anticipate before this quarter, so we're gonna try and fix those before before winter quarter, and then by the end of the first week next quarter. So, for instance, the reservoir, we aren't really, we're not running too well right there. We have to hold our piping into the reservoir, so we're hoping to not have to have a person having the task of holding our hosing into the reservoir. So we're going to evaluate that, try and come up with a solution to that. We're also going to come up with a method of charging our accumulator, since our accumulator for RP is not currently in use, since it's been pre-charged upon receiving it, and the valve is not quite an American standard tank valve. So we're going to have to figure out a way where we can discharge it and charge it up to a pressure that we want. And then our MyoWare we need to purchase. We also have to purchase a new relief valve, since if we want to actually have an actuation, we have to plug our relief valve in order to get the actuator to run. So that's another thing that we have to solve by next quarter. And then of course, we have to purchase all that again. And we want to get a good structure for our frame in the forearm and through our bicep. And that's all things that we would like to have happen sooner rather than later.
I hold on to you.